we want to find the fluid force on the bottom of this tank. So this is the aquarium tank filled with water. It's 2 meters wide. It's 90 centimeters deep. I don't know, long, wide. I don't know. People use different names for things. It's 2 meters long. It's 90 centimeters wide. It's 120 centimeters tall or deep, I suppose. We want to find the fluid force due to pressure on the bottom, on the front side, and on the right side. So, and the person who sent me this question or wrote this question, I think you had some of your numbers kind of mixed up. So let's be super duper extra careful. The bottom is super straightforward because the bottom, all of it's at the same depth. So for the bottom here, the fluid force is the area of the bottom, and we do want to measure things in meters. So it's going to be 2 meters times 0.9 meters times the depth, which is 120 centimeters or 1.2 meters, times the density of water, which is 1,000 something. I forgot the units. It's what, 1,000 kilograms per cubic meter. Does that sound? That sounds like way too much. Let me double check the numbers here. Feel like I'm saying the wrong thing. Let me double check. Nope, it's 1,000 kilograms per cubic meter. Okay, but that's the mass density. And I want the weight density, right? So this should be the weight density, meaning how much weight per how much volume. This is mass per volume. I need to multiply by 9.8 meters per second squared. So that would be the fluid force due to pressure for this particular problem, for the bottom. And I don't think we need to multiply this out. I'm sure everyone can multiply, I mean, on a calculator, 2 times 0.9 times 1.2 times 1,000 times 9.8. No big deal.
James?
Yeah.
The 9.8.
Mm-hmm.
What was that for again? Or what did that like? Because
that's so when you're talking about how much something weighs, you're talking about its mass times the acceleration due to gravity.
Oh, yeah. Okay.
So the mass of the water is 1,000 kilograms per cubic meter, which is really the mass density. The weight of the water is 9,800 newtons per cubic meter, or the weight density is 9,800 newtons per cubic meter.
Okay.
So yeah, when it's the metric system, you have to multiply your kilograms by gravity. In the US system, if you're given pounds, which you almost always will be given pounds, they've already accounted for multiplying by gravity with that measurement.
Okay, that's okay. Thank you, James.
So now I want to find the fluid force due to pressure on the front side. And the problem is, unlike the bottom, the front side, things are at different depths, right? This slice here, not really a slice, this strip on the front side is at a different depth than this strip here. And what that means is there's different amounts of force acting on them due to pressure, right? Here, there's less water above this than there is here. Now, there's a thing they talk about in the book, like where if you talk about something being on its side, there's still as much pressure or fluid force due to pressure acting on it as if it were oriented like this. So it doesn't matter if it's like this or like this or like this. Physics tells us that the pressure on it just depends on how deep it is and how much area there is. It doesn't matter if it's oriented like this or like this. So this thing that's oriented this way, the force on it due to pressure is purely a function of its depth and its area. So the thing is, the depth can be any depth between as low as y equals 0 and as high as y equals 1.2. Now, sorry. Apologies. Yeah, that's interesting. I hadn't really. So I'm just saying. I always like to set it up as the bottom is y equals 0 and the top is y equals 1.2. But I suppose it would not be incorrect to think of it the other way. Whereas you could also set it up as the top being y equals 0 and the bottom being y equals 1.2. But either way, we're going to figure it out. So let's set them up. I'm gonna set up one way. So I'm gonna say, doing it this way, that measured from y equals 0, this distance is y. You always want to have y measured from where y equals 0 is. So it would be really, really incorrect to call this y. This is y. This, on the other hand, is 1.2 minus y. But I want to be super extra clear. When you're drawing your kind of strip that's anywhere in the shape you're dealing with, it's always at some variable distance from what you actually care about. In this case, we're calling it y. So the area of that strip is the length of the strip times the depth times the thickness of the strip, the width of the strip, which is dy meters, times the depth, right? So I have the length, I have the width. Now I'm going to have the depth, which is going to be, well, it's going to be variable. It's going to depend on how high it is. It's going to be 1.2 minus y times density times 9.8. But that's just the fluid force due to pressure on this strip. I want to find the fluid force due to pressure on all the strips from as low as y equals 0 to as high as y equals 1.2. So that would be how you find the fluid force due to pressure on this front part here. You do the integral from 0 to 1.2 of 2 times dy meters. And actually, I'm going to erase the meters so we don't have all this kind of confusing stuff in there. 2 times dy times 1.2 minus y times 1,000 times 1.8. And let me use dots for my multiplication just so it's less confusing. I will mention, just because I think it's worth mentioning, if you set it up this way instead, where the top was y equals 0 and the bottom was y equals 1.2, and you said, okay, well, now this distance is y, the depth is y. You set it up this way, your fluid force due to pressure is going to be the integral still from 0 to 1.2, because the depth still goes from 0 to 1.2, of 2 times dy times, instead of 1.2 minus y, it's going to be just y times 1,000 times 9.8. This will end up being the same, right? Essentially, both of these. So if you factor out the 9.8, the 1,000, and the 2, let's see, 9,800 times 2 is 19,600. This is equal to 19,600 integral from 0 to 1.2 of y. And this red one here is same coefficient, 19,600 integral from 0 to 1.2 of 1.2 minus y. Graphically, here's the difference between these. So I'm going to draw both these integrals real quick. I don't want to erase this. I was going to use this. Sorry, I'm not going to draw them. Basically, I was going to point out that the integral from 0, like if you've got like, if your y-axis is like this, and you're going from 0 to 1.2 of y, you're getting that area of that triangle. And if you do it the other way, which I've mixed up the colors, sorry. If you do this one, 1.2 minus y is this triangle, which has like the same exact shape. It's just flipped over. So this integral from 0 to 1.2 of y, and this integral from 0 to 1.2 of 1.2 minus y, here's 1.2, right? Here's 1.2. They're the same area. I don't want to do these integrals because they're not that hard to do. So yeah, now the only difference between these ones and the smaller window ones is that the smaller window the depth is still the same. The depth is still, if you're using this red one, is still 1.2 minus y. The area of my strip is slightly different. Instead of being 2 meters times dy, it's going to be 0.9 meters times dy. So this smaller window is going to have the same integral from 0 to 1.2, but instead of 2 times dy, it's going to have a 0.9 times dy. times 1.2 minus y times 1,000 times 9.8. Fun. But so the fluid force due to pressure on this front region and the fluid force due to pressure on the smaller side region are essentially the same integral, just the only difference is how long it is. This one's 0.9 meters, this one's 2 meters. That's it, that's the only difference. Questions about that? We'll go fix my picture on the other side. I didn't totally destroy it, but I did kind of mess it up. Okay. All right. So again, the whole idea with fluid force due to pressure is it's just depth times area times the other thing. Sorry. Oh, times density. So let's look at this next one. This is kind of like the dam problem. So you've got this dam, and the dam. How do they write here? They use some words that are nice. The dam on this river is built so that the wall facing the water is shaped like the region above the curve, y equals 0.5x squared, and below the line, y equals 200. So this shape here is the dam itself. And then we want to find the fluid force due to pressure on the dam from the water that happens to be 38 meters below the top of the dam. And I especially think in this case, you definitely want y equals 0 to be the bottom of the dam, because it's really going to be nicest if the vertex of the parabola is at the origin. If you start changing things around and calling like this y equals 0 and this y equals 200, then this equation actually changes, which is unfortunate. So it's usually I'm orienting things in kind of a typical way. So what I want to do is I want to find the fluid force due to pressure on a strip. So I'm going to draw some representative strip. And I'm going to say that strip is at a height of y. And I want to know for that strip, I want to know the fluid force on the strip, which is just going to be the area of the strip times the depth of the strip times the density of the force acting on it, which is water. And sorry, things are measured here in meters. Yeah, this is 200 meters. This is 0 meters. This is 38 meters below the surface. Okay. So the density, right? We know the density is going to be 1,000 kilograms per cubic meter times 9.8, or just 9.8, whatever, just 9,800. Right? I don't care about the units. Although the units would be right. The units would be dumb. The units would be kilograms per meter squared second squared. Okay. So that's our density. What's the depth? Well, it's a good question. How far below the water level is this strip? So I don't want to go from here to the top. I want to go from here to where the water is. Well, that water level is 38 meters below the top of the water. So 200 minus 38 is 162. I feel like that's not the number I meant for it to be. No, I guess it is. Yeah, that's right. Okay. Yeah. So this is going to be the water level is at a height of 162 meters above the ground. And the depth of this is going to be 162 minus y. Okay. So now here's what we typically do for the area. So the area is going to be this length. So I'm going to call L for a minute. Times dx. So I feel like I need to do this in terms of x because I've got a dx. So I'm going to say, well, this half of that is just x. So is that really? I'm making a small dumb mistake here. Why am I saying dx? It's not dx, it's dy. That was really not smooth of me, right? That's definitely that small width there is a small change in y, not a small change in x. So the area of this is looking like 2 times x times dy. What's the problem here? I'm going to integrate with respect to y. I don't want to have x's. So I need to take this equation and say, okay, well, I'm going to solve for x. Looks like x squared equals y divided by 0.5, which is just 2y. So it looks like x is going to equal the square root of 2y. Stop me if you have questions. So the area of this strip is going to be 2 times the square root of 2y times dy.
Wait, James.
Yeah.
So how did you rearrange again x squared equals to y over 0.5?
So I'm just taking so they gave me the equation, right? The dam has the shape y equals 0.5 times x squared. And then I'm solving for x, so I divided both sides by 0.5. So x squared equals y divided by 0.5.
Oh, okay, yeah. It's because I didn't see the 0.5 like when you wrote the original y.
Sure, yeah, I can see how it'd be hard to see that. I'm having a hard time seeing it myself. So, and then dividing by 1/2 is multiplying by 2. So x is the square root of 2y. Okay, so then the fluid force on my strip is going to be this area times this depth times this density. So the fluid force is going to be that times that times that. It's going to be, I'm going to write it as 9,800 times 162 minus y times 2 times the square root of 2y dy. And then we have to integrate, right? Because that's just the fluid force on this strip, and I want the fluid force on all of the strips, all the way up to the top. So I want the fluid force on all the strips as low as y equals 0 and as high as y equals 162. So it's kind of interesting here, knowing that y equals the whole thing is 200 meters high doesn't actually really matter. As far as we're concerned, the dam could be 162 meters high and we'd still get the same result because the fluid force due to pressure on that part of the dam isn't changing because there's more dam up here or not. All right, this is kind of gross. Let's do it. So I've got 9,800. Yeah, is this really? Yeah. So 9,800 times the integral from 0 to 162. If we multiply this out, so 162 times 2 is 324. So I got 324 times the square root of 2y, which I'm going to write as the square root of 2 times y to the 1/2 minus 2 times the square root of 2 times y to the 1/2. Are there questions about this before I erase stuff and actually calculate the integral?
How did you get the 2x or the how you changed from 2x and you went to 2 times square root of 2y on the right hand side of the whiteboard?
Sure. So this distance is x, right? But I want it to be in terms of y. So I said, well, I know that. So for example, just kind of point something out, right? Like if, for example, I don't know, let's pick something that's kind of nice. Sorry. 1 second. If, for example, we were at a height of 72. Let's say we were 72 meters high, right? Well, I want to know how far out I am. And I could say, well, I'm X out, but I can also find X in terms of Y. So I could say, well, if Y is 72 and is equal to 0.5 X squared, then if I divide by 0.5, X squared is 72 divided by 0.5, which is times by 2, that's 144. And then X is going to equal the square root of 144, which is 12. So that's how I'm getting X. I'm saying X is the square root of Y divided by 0.5. That's exactly.
And why is it 2 times?
What's that?
Why is it 2 times that?
Because the length X is just this length here, right?
Okay, so it's the
From
opposite.
the y-axis to wherever, and then I'm doubling that to get that.
Okay, thank you.
If you wanted to, another way that would result in the same thing would be to say that it's this right side is X equal to the positive square root of 2y, and the left side is X equal to the negative square root of 2y, and then you could subtract them and you would get 2 times the square root of 2y, which is exactly that. Okay, so now for the not fun part. If we calculate this, it's going to be real ugly. So we're going to get 9,800 times 324 times root 2 times y to the 3/2 times 2/3 minus 2 root 2 y to the 5/2 times 2/5. That's terrible. From 0 to 162. And then you plug it in and you would cry. Yeah. Oh. That's interesting. And well, anyway, so yeah, you plug it in, it would be awful. And that's kind of it. Doing something like this in grade or in web work is not super duper nice, but it is a thing. So let me look at the next problem. Let's do another one and then maybe we'll move on. Okay, so let's say we have something like this. Sure. Thinking for fluid force due to pressure, it's all about everything being submerged to the same depth. If you have things at different depths, you have to. That's when you have to integrate. So let's say we have a circular window. Window with a radius of 2 feet is submerged 100 feet below the water. And it's in a right? Like for example, you're on a submarine, right? And you're looking out a window, and that window is 100 feet below the surface of the water. How much fluid force on it? Okay, so let's draw ourselves a little picture. We've got here's the water. And the thing is, if I say something's submerged 100 feet below the water, I'm thinking of the bottom of it being 100 feet below the water. Right, so my window here, the bottom of it's 100 feet below the water. So I'm going to say that, well, so here's the wrong way to do this. I don't want to say that this is y equals 0 and this is y equals 100. It's going to make my equations really challenging. The best way to do this is to actually say that the center of the circle is where y equals 0 is. So this then becomes, well, my radius is 2, This is y equal to -2. And this is going to be 2 less. This is going to be y equal to 98. So we're going to work with that framework instead. Why? Because it's going to be easier. So, yeah. So let's say we have a strip right here. Now I know what's the fluid force on that strip. Okay, well, let's say that strip is at a height of y, above y equals 0. So the force on the strip, once again, is going to be area times depth times density. In this case, since I'm doing things in terms of feet, we know that the density of water is 62.5 pounds per cubic foot. And we don't have to multiply by gravity because pounds already accounts for that. So we just need the area of the strip times the depth of the strip. Well, the depth of the strip is easy. The depth of the strip is just 98 minus y. The area is also, well, the area is a little bit challenging. So I'm going to do the same thing I did before. I'm going to kind of cut this down the middle. I'm going to say that this length here is x, and my area is going to be 2x times dy. But of course, that's problematic. I want y's, not x's, if I've got dy. So I'm going to write an equation. The equation I'm going to write is going to be, well, I see the Pythagorean theorem. I see that this length is 2. This length here is y, and this length here is x. So that x squared plus y squared equals 2 squared. And solving for x squared equals 4 minus y squared. X equals the square root of 4 minus y squared. Okay. So now what? Well, the force on my strip is equal to 2 times the square root of 4 minus y squared. Times the depth, which is 98 minus y, times the density, which is 62.5. How are we feeling about the setup? Okay, fine. So let's do the integral. Let's go ahead and do it on the other side, just so in case we want to come back to this. So I'm going to do the integral. So I'm going to do the integral of this area. I forgot the dy. This area times depth times density. And then my strips are going to go as low as y equals -2 to as high as y equals +2. Okay. So we're going to be doing the following integral. Now this is where some cool stuff happens. This integral is going to look super terrible. It's going to be really easy. So you're going to have the integral from -2 to 2 of 2 times the square root of 4 minus y squared times 98 minus y times 62.5 dy. Let's make it a little bit easier. 2 times 62.5 is 125. Let's figure that out. This is 125 times the integral from -2 to 2. And let's distribute. Let's distribute this square root of 4 minus y squared to 98 and to y. 98 times the square root of 4 minus y squared minus y times the square root of 4 minus y squared. And now let's write that as two integrals. That's 125 times the integral from -2 to 2 of 98 times the square root of 4 minus y squared dy minus the integral from -2 to 2 of y times the square root of 4 minus y squared dy. All right. Can anybody tell me what this integral is equal to? It's 0. Why is it 0? What kind of function are we integrating from -2 to 2? An odd function. So since that's odd, we can automatically be like, oh, that's going to be 0. Or you could do a u sub. You could let u equal 4 minus y squared, and du would be -2y dy. And so the -1/2 du would be y dy. And when we change that, whatever, change that, whatever. But if we change the limits of integration, if y is 2, 4 minus 2 squared is 4 minus 4, which is 0. And if y is -2, 4 minus -2 squared is 4 minus 4, which is 0. So the integral from 0 to 0 is going to be 0. This one is also easy because the square root of 4 minus y squared is the right half of a circle, right? X equals the square root of 4 minus y squared is a circle, half of a circle. So this here is going to be 98 times 1/2 pi times the radius of that circle squared, which is not too terrible. So we end up getting 125 times 98 divided by 2 is 49. Actually, you should just cancel it too. 98 times 2 is 196. So you get 125 times 196 pi. Kind of neat. Sometimes things work out really nicely like this, but you have to, but I will tell you, if you'd set this one up so that the bottom was 0 and the top was 100, or the top was 100, 0 and the bottom was 100, it would not have worked out very nicely. You really want to set it up so that y equals 0 is right here. Yeah. Okay, let's talk about moments and center of mass and stuff. Oh, yeah. It's Laura's good. So, I'm talking about center of mass. We're really just talking about a balancing point. Go ahead and find word method. There. So, yeah. Sorry. The picture I've got looks kind of funky. I just want to see one thing. Oh, that's interesting. Okay. So, how do I say this? Let's talk very basic for a second. So let's say we have a seesaw, and we have a larger mass here being balanced by a smaller mass that's further out. So here's what it means for these to balance. If this is balanced, it means the moment is equal to 0. The moment is just the tendency to swing one way or the other. If the moment is positive, we think of it as swinging to the right because we think of the right side as the positive side. The moment is negative, we think of it as swinging to the left. When it's balanced, the moment is 0. And here's what that means. It means that, so I should kind of say, the tendency to swing one way or the other is determined by the distance that something is from the fulcrum. So the overall moment of this system is how do I want to say this right? Is m times d1 plus capital M times negative d2. It's negative because it's to the left, right? Left, right, left, right, left, right. Because it's over on the other side, right? If we're thinking of this is like the center, for example. Is that really what I want to say? Actually, let me think about this for 1 second. Yeah, well, we'll be more specific in a moment here. And this is supposed to equal 0, so that you get m times d1 equal to m times d2. So that's kind of a balance system, right? Where the moment enacted by one object is balancing out the moment enacted by another object. Now, how does this relate to the center of mass? Well, let's say we have these two objects somewhere living on the x-axis. Here's object 1, mass. Let me use some real numbers. Let's say we've got object 1 sitting on the x-axis on the teeter-totter that is the x-axis. Let's say it has a mass of, I don't know, 5 kilograms, and it's located at x equal to 2 meters. And then further out, over here, x equal to, I don't know, 8 meters, we have a mass of 2 kilograms. So what is going to be the center of mass? So the center of mass is going to be where this whole system balances. And it's probably going to be closer to the 5 kilogram thing than the 2 kilogram thing, because the 5 kilogram thing needs to have less of a lever arm to have less moment for it. So it's probably going to be something like this. I'm going to say that's my center of mass is about right there. Okay, so let's actually set the equation. Let's say that this is my center of mass. So let's call it x bar, which is the typical name for the center of mass. What I'm going to find x bar is I'm going to say, well, I want the moment around x bar to be 0. So I'm going to call this distance, what do I want to call this? Let me make sure I get this right. We're going to call this d1, this d2. I don't know if the distances are yet, right? Because I haven't found my center of mass. So what I'm going to do is I'm going to say, well, actually, let me, sure. Sorry, my cat just came. Let me 1 second. Cat, I want you to not be in here. Yes, I know you want to be in here, but then you're going to want to leave. Sorry. So sorry, brain work for a second here. Yeah. So sorry, my brain is like kind of thinking about how it's supposed to work. You want, right. So you want these moments to balance out. So you want that, and I've forgotten how this works. So brain. So the moment of this around the x-axis is going to be, gosh, there's some calculation my brain is not remembering how to do, and I have to think about it for just 1 second. Sorry. What am I missing here? So let's say that this is, okay, yeah, sorry, I got it here. This distance is 8 minus x bar. There we go. And this distance is x bar minus 2. Got it. So then the moment around this, which we want to be 0, should be this moment plus this moment equaling 0. So we should have that 2 times 8 minus x bar plus 5 times x bar minus 2 should equal 0, assuming I've done this correctly. Okay, let's solve for x bar. So let's see. Guess we can multiply it out. I've got 16 minus 2x bar plus 5x bar minus 10 equal to 0. So I've got 3x bar. 16 minus 10 is 6. And this is looking bad. I've definitely made a mistake somewhere. Ugh, hate when I make a mistake for you guys. Sorry. What did I do? What I probably needed to do was, yeah, I know what I did wrong. So what I did wrong was I should have set these equal to each other. Apologies. I apologize. I will fully admit this material is always the stuff I'm kind of the shakiest on. It's just kind of like, right? These moments should equal each other because, right, that's a positive mass times a positive distance, right? This is 8 minus x. This is a positive mass times a positive distance, x minus 2. Okay, now this should work out just fine. So bringing everything to one side, let's bring everything to the right. We've got 0 equal to 5 times x bar minus 2 minus 2 times x bar, sorry, 8 minus x bar. Okay, don't worry, we're gonna see something that's worthwhile, I promise. We're almost there. So I've got 5x bar minus 10 minus 16 plus 2x bar equal to 0. 5 plus 2 is 7x bar minus 10 minus 16 is minus 26 equal to 0. So 7x bar equals 26. X bar equals 26 over 7, which is a little bit more than, it's almost 4, which is definitely closer to that, right? Because halfway between 2 and 8 is 6. Now, how do we get this calculation? Well, here's what this calculation really is. It's the total moment of the system, right? The total moment being 2 times 5 plus 8 times 2 divided by the total mass of the system. So I want to make this, and I should say, I will try to make this more clear as we go along. But when you're finding the center of mass of something, you're taking the total moment and you're dividing by the total mass. That's it. You can see this if you look at the formula more generally. I was trying to pick numbers to make it easier. I feel like that didn't make it easier. But if we look at this, a little more generally, and I know, no, I think this is worthwhile. So if I look at this again, but instead I say I've just got big M here, or really M1 and M2 here, and the center of mass is, you know, some x bar, and this distance is, and this is where I have to be super careful. Let's just talk about the distances from the x-axis. This is distance 1. This is distance 2. This distance here is x bar minus distance 1. This distance here is distance 2 minus x bar. So then for the system to be balanced, this moment should equal that moment. So M1 times x bar minus D1 should equal M2 times D2 minus x bar. Let's solve for x bar. So bring everything to the left. M1 times x bar minus D1 minus M2 times D2 minus x bar equals 0. Multiply it out, M1 x bar minus M1 D1 minus M2 D2 plus M2 x bar equals 0. Keep the x bars on this side. So m1 x bar plus m2 x bar equals positive m1 d1 plus m2 d2, or R, it sounds like R2 d2. And then factoring out the x bar, you get x bar times m1 plus m2 equals m1 d1 plus m2 d2. And then finally, x bar is equal to m1 d1 plus m2 d2 over m1 plus m2. But look, m1 plus m2 is the total mass of the system, and m1 d1 plus m2 d2 is the total moment of the system about the y-axis. Right, so this is the moment around the y-axis. Right, it's the mass times the distance from the y-axis, and the mass times the distance from the y-axis. So I want to be, so I will mention this formula kind of always confused me when I first went. I was like, how does knowing the moment around the y-axis tell you where the center of mass is? Well, it's because it comes out of this formula, right? If you set these two moments equal to each other and you're trying to solve for x bar, it exactly happens to be the x bar is going to be the moment around the y-axis, which is the likelihood for it to swing around the y-axis. So in this case, since everything is on the right of the y-axis, the moment's totally going to be a positive number because it's very likely to swing around that way. And then divided by the total mass. That's it. I mean, it's going to get more complicated, but mathematically speaking, when you're trying to find a center of mass, it is just the moment divided by the mass. That's it. Okay, so let's look at some examples. If you got questions, feel free to stop me.
Yeah, James, I was just quick question. I was wondering if you could flip. Yeah. That's. Okay. Okay. Thank you, James.
You're welcome. Okay, so let's look at this example. So I want to find the center of mass of a thin rod with a length of 10 centimeters with density equal to x squared grams per centimeter as measured from the left end. So as you go further to the right, the bar is heavy, right? So you've got this thin rod. Over here, the density, I mean, I guess would be 0, which would be kind of silly, okay. Right, so the density here is 0. And over here, x equals 10, and the density is 100 grams per centimeter. Okay. So, and we're kind of, again, right, we're thinking about measuring. Now, I know this is kind of silly, but we're thinking about measuring the moment around the fulcrum being right here. So if the fulcrum was right there, the moment of the system is going to be very positive, right? If you try to balance this thing on that fulcrum, it would definitely swing that way, right? On the other hand, if the fulcrum was, say, like right here, the thing would probably swing that way. If it swings that way, your moment is negative. If it swings that way, your moment is positive. But if I'm thinking of this, right, I want the moment to be positive so that my center of mass ends up being a positive number somewhere between 0 and 10. So the center of mass, now I can't just add up the moments, so I have to integrate the final moment. So I'm going to add up all of the masses times their distance to the fulcrum, right? So the moment, which I'm going to call my, because it's the moment around the y-axis, divided by the total mass, So the moment around the y-axis is just the integral of the mass times the distance of that mass to the fulcrum. Or as I like to call it, the length of the lever arm. So if we've got a small like slice right here of your rod, that slice has a mass of, well, it's the thickness of it, dx times the, sorry, brain, times the, where'd you go? Times the density of it, which is just x squared grams per centimeter. Okay, it's dx centimeters, it's x squared grams per centimeter. So that mass there is going to be x squared grams. And the distance is going to be just x divided by the mass, which is just the integral of the mass of our slice. So that's going to be the integral of x squared times x times dx divided by the integral of just x squared times dx. So the mass is just the integral of the density. The moment is the integral of the lever arm times the density. From 0 to 10, from 0 to 10. So that's going to be the integral of x cubed. That's going to be x to the 4th over 4 from 0 to 10 divided by this one's going to be x to the 3rd over 3 from 0 to 10. So you're going to get 10 to the 4th over 4 divided by 10 to the 3rd over 3, which is 3 over 10 to the 3rd. 3 of those cancel with 3 of those, so you get 30 over 4, which is 7.5. So the center of mass is like 3/4 of the way. Right there, that's your center of mass. Kind of cool. Oh, sorry, someone typed something. You cannot combine the two integrals. That's an excellent question, Katie. And the answer is a hard no. You definitely cannot combine those integrals. It will definitely not come out the same. I'm imagining you're asking like, could I divide these and just have the integral of x? How I wish that were true. It is not true, right? Definitely the integral from 0 to 10 of just x would be x squared over 2 from 0 to 10, which would be 100 over 2, which would be 50. Yeah, totally unfortunate, but yeah, that's the way it goes.
What?
All right, go ahead. All right, let's look at a more typical example. Let's find the centroid of this plate. So find the centroid, and the centroid is just the center of mass, assuming that the density is constant. That's all it means. So find the centroid of the thin plate bounded by y equals x and y equals root x. So this plate here. Okay. So the centroids, so there, I should say, first of all, the centroid has an x and a y coordinate. So I have to find the moment around the y-axis and the moment around the x-axis. So, and I want to point out, right, the moment around the y-axis, that tells us the likelihood to swing around the y-axis. And if we divide that by the mass, that's going to tell us how far from the y-axis we should have our center of mass. So, right, wherever it is, I don't remember what the number is exactly. Let me take a look here. Sure. So our x bar is going to be the likelihood to swing around the y-axis divided by the total mass. Whereas our y bar is going to be the likelihood to swing around the x-axis divided by the total mass. So typically when you're finding the centroid of something, you have to find three things. You have to find the moment around the x-axis, the moment around the y-axis, and the total mass. So let's start with the mass. Oh, and we should find what I didn't start with these functions. We're sorry. This is y equals root x. This is y equals x, which clearly intersect at 1, 1. So let's take a look here. Yeah. Oh, here's some good words, I should say. Think of the plate as a door attached to the y-axis. My, or the moment about the y-axis, measures the tendency for the door to swing about the y-axis. Mx measures the tendency to swing about the x-axis. The thing that I always have to kind of remember is that, like, if you look at this, you're like, well, what do you mean the tendency to swing about the y-axis? Like, it's vertical. Why would it swing either way? But the point is, you're supposed to think of this as the x-y axis being flat. So if you put this down flat, then the tendency to swing around the y-axis is clearly going to be in this direction because it's purely on the right side of the y-axis. Okay, so let's find all the things. The mass is going to be the integral of the density, which is constant, times the area, times, right, that's going to be just times the area, right? That's it. I'm like, that's the mass, integral of density times the area, which in this case is going to be the integral of the density times, okay, the area of that strip is going to be, if I use a vertical strip, the area of that strip is going to be the top function minus the bottom function times the width of that strip, which is dx. From as left is 0, as right is 1. So let's see, we're going to get, I'm going to integrate this. I'm going to get the density, antiderivative x to the 1/2 is 2/3 x to the 3/2 minus x squared over 2 from 0 to 1. That's going to be the density times 2/3 minus 1/2, which is going to be, what do we got here? Why does it look different than what I have over there? Oh, it's because there's an x there. I see. So 2/3 minus 1/2 is 4/6 minus 3/6, which is 1/6. So you get delta divided by 6. Okay, so that's our mass. Let's go ahead and find the moments. So here's what I would encourage you to do. I really don't like the weird alternate formula, but sometimes we have to use it. So for the moment around the y-axis, I'm going to use a vertical strip, because for a vertical strip, all of that strip is the same distance to the y-axis. So the moment around the y-axis is the integral of the mass times the, I call it the lever arm, which is going to be, so the mass is the same as it was there. It's the density times the area, right? That's the mass. So it's still going to be the density times the area, which is root x minus x times dx. And the lever arm is just how far it is from the axis, which is x. So this is very much like with the surface area. If you're going around the y-axis, the radius for the surface area is x. If you're going around the y-axis, the lever arm for a moment is just x. So, and that's still from 0 to 1. So I'm going to get the density, and let's just do this real quick here. I've got root x minus x times x. Root x times x is x to the 3/2. X times x is x squared. And then if I integrate that, I get x to the 5/2 times 2/5 minus x squared integrated is x cubed over 3 from 0 to 1. So I end up with 2/5 minus 1/3 times delta, which is going to be 4/15. Ooh, that looks, oh no, 6/15 minus 5/15, which is 1/15. So delta over 15. Okay. And so what I want to point out is that when you are finding a centroid, the densities are going to cancel, right? Because the x bar here is going to be the moment on the y-axis, which we just found to be delta over 15, divided by the moment around the mass, which is delta over 6. And the densities just cancel because they're constant. So when I calculate this, I usually just ignore it. When I calculate a centroid, I almost always just ignore the density. That's going to be 1/15 divided by 1/6, which is 6/15, which is 2/5. Okay. Now let's find the moment around the x-axis. So I'm going to erase my mass here.
Oh, wait, James, I have a quick question.
Sure.
Could you explain again the time how you distinguish what lever arm to use? Like,
Sure. So if I'm going around the y-axis, the lever arm is x. If I'm going around the x-axis, the lever arm is y.
oh, okay.
But there's more to it than that. So I'm going to talk about it in two ways. So if it were up to me, I would do the moment around the y-axis using a horizontal strip. So the moment around the y-axis would be, well, again, it's the integral of the mass times the lever arm. The mass, once again, is the area times the width. But in this case, since it's horizontal, the area is the right function minus the left function. So it's y minus y squared, right? Because the right function is x equal to y, and the left function is x equal to y squared. The width of the strip is dy times the density. Let's put the density out here. Right, so there's my mass, density times length times width. And the lever arm, well, for measuring to the x-axis, because we're going around the x-axis, the lever arm is just y. Okay, so that's going to be delta times the integral of y times y is y squared, y times y squared is y cubed. We're going from 0 to 1, right? Because it's 0, 0 to 1, 1, so the limits don't change. And that's going to end up being delta times y to the third over 3 minus y to the fourth over 4 from 0 to 1. And when you plug in 1, you get 1/3 minus 1/4, which is 1/12. So this ends up equaling delta over 12. And then your y bar is mx, which is delta over 12, divided by your mass, which is delta over 6. And this ends up being 6 over 12, which is 1/2. Okay, so here's the thing. This is lovely and the nicest way to do it. However, sometimes you're going to be given a problem like this where you're also going to have a variable density in terms of x. And if your density is in terms of x, you're not allowed to integrate with respect to y. It just doesn't work. So we have to do something else. So what we have to do is the following. We have to use the alternate dumb formula. So another way to find the moment of this region around the x-axis is to use a vertical strip. And to say, okay, I want to find the moment around the x-axis. Well, it's still going to be the integral of mass times the lever arm. The mass is still the same. The mass is still area times density. But we're doing it in terms of x, right? Because we have a vertical strip. So the mass is still the density times root x minus x. Times dx. There's your mass. Okay. The lever arm, on the other hand, well, that's where things get more complicated. Because this strip is not one specific distance from the x-axis, right? It's a lot of distances. Here's what we can do. Because of the symmetry of a rectangle, we can say, I'm just going to pretend like the entire mass is situated at the center of that rectangle. So I'm going to say all the mass is right there, halfway between the top function and the bottom function. So how do I find how high it is? Well, I'm midway between two functions. I'm at the midpoint of two functions. I'm at the average of two functions. So this function being y equal to the square root of x, and this lower function being y equal to x, this height is the square root of x plus x divided by 2. So whenever you're trying to find the lever arm and you have your strip being perpendicular to your axis of rotation, you have to use this kind of silly formula. Now, here's how this shakes out. You have root x minus x times root x plus x. That's root x squared minus x squared. So you end up getting 1/2 times the integral of your density times your top function squared minus your bottom function squared. And that's the general formula, right? If you've got some, more generally, right? If you've got some like f of x, g of x, and you want to find the moment around the x-axis, the moment around the x-axis is 1/2 the integral of f of x squared minus g of x squared dx. Throw in the density. It is the same. Let's check and see. Limits of integration is 0 to 1, 0 to 1. If we do this, we get 1/2 delta integral from 0 to 1. Square root of x squared is x squared is x squared. Integrating this, we get 1/2 delta times x squared over 2 minus x cubed over 3, 0 to 1. So we get 1/2 minus 1/3, which is 3/6 minus 2/6, which is 1/6. So you get 1/2 delta times 1/6, which is delta over 12. Just like it was here. So if you can use either way, I recommend that, but sometimes you're stuck using the terrible kind of half of a function square minus another function square formula, which is not my favorite, but it does come up. Wait, what does it say on mx? Mx is equal to delta over 12. And I accidentally wrote that as my up there. I'm sorry about that. I know there's something, yeah. Oh, on the other side, sure. On the other side, it says, it says the same thing. But here it says mx is 1/2 delta, sorry, 1/2 the integral of delta times f of x squared minus g of x squared. Right, so you have, to get the mass, you do the top function minus the bottom function. And to get the lever arm, you do the top function plus the bottom function divided by 2. And then when you multiply those together, so if you have, right, f minus g times f plus g over 2, if you factor out the 1/2, that gives you f minus g times f plus g, but f minus g times f plus g is just f squared minus g squared. That's what you get. So these values would not be the coordinate points. The coordinate points would be x bar is 2/5, the delta over 15 divided by delta over 6, and y bar is 1/2, the delta over 12 divided by 1/6. So the coordinate here would be 2/5, 1/2. That would be your centroid. Let me get some more water. Grab it. Other questions? Okay, let's look at another example. So let's find, I'm gonna do an easy one and then kind of a harder one. So let's say we have the region, yeah. So I want to find the center of mass of this region. This is y equals 4 minus x squared from -2 to 2. This is 0, 4. And where the density at x is x squared. Okay, so for this one, we cannot use y because the density was given in terms of x. So we have to find three things. We have to find the mass. We have to find the moment around the y-axis, find the moment around the x-axis. So let's find the mass. So mass is going to be the integral from -2 to 2 of 4 minus x squared times x squared. Right? It's the area of my strip. Well, really, I should say it's the mass of my strip, right? It's the area of my strip, which is 4 minus x squared times dx times the density, which is x squared. So that's going to be, this is probably going to be a little bit grosser than I intended it to be, but let's go ahead and do it. It's the integral from -2 to 2 of 4x squared minus x to the 4th. I would point out that this is an even function, so let's just do 2 times the integral from 0 to 2. That'll work just fine. That's going to be 2 times 4x cubed over 3 minus x to the 5th over 5 from 0 to 2, which is going to be 2 times, let's see, 32 thirds minus 32 fifths. That's going to be 64 times blah. 1/3 minus 1/5 is 2/15. So 128 fifteenths. Nice. All right, now here's the thing. What about the moment around the y-axis? Well, let's find it. So it's going to be the integral from -2 to 2 of my function, which is, sorry, my function times my mass, my mass times my lever arm. Okay, the lever arm is just x, right? It's the distance from the mass to the axis that we are momenting around. So the mass of that is the same as it was here, right? It's still the area of the strip, 4 minus x squared times dx times the density of the strip. Oops, I forgot the x squared. 4 minus x squared times x squared times dx, right? That's the whole mass of the strip. And then the lever arm is just x. And now here's what ends up working out here. This ends up being actually 0 because that's an odd function. That's the integral from -2 to 2 of 4 minus x squared times x cubed, which is just 4x cubed minus x to the 5th. Which is 0. What I want to point out is if it was the centroid, it would also be a 0 coordinate for x, right? So x bar is going to be 0 divided by 128 over 15, which is 0. And what I want to say here is like if my density had been something weird that wasn't x squared, like if my density had been x cubed, this wouldn't cancel out this way. So if you've got symmetry and constant density, fine. If this was symmetric and the density was constant, the x coordinate would be 0 because it's equally balanced on either side. But if the density was something like, x cubed, where, things don't really do the same thing, it would be weird. So x cubed might be kind of weird because of the negative places, but if it was like x squared plus 2 or something, right? Where the left side and the right side didn't have the same thing, it wouldn't balance out. Okay, so let's go ahead and find mx. So mx here, we have to use the formula where we're again, well, I mean, so again, you should think about what's happening here, right? It's going to be the integral from -2 to 2 of the mass. There's the mass. Times the lever arm. But the lever arm is that distance there, which is half of how high the function is. In this case, since the bottom is 0, it's just half of the function. So it's going to be half of 4 minus x squared. That's your lever arm. So in this case, I don't really need to write it this way, but you could write it as 1/2 the integral. Damn, I had a room, but not enough room. 1/2 the integral of the density times the function squared. It's really the top function squared minus the bottom function squared, but the bottom function is y = 0, so we don't have that, right? It's I erased that formula, sorry. Dx, and that's your density. That's your f of x squared. Can you explain? So I have like part of the chat covered up idiotically. Sure, the 1/2 is because, right, we're saying if we're going around the x-axis, I want to find the moment of this region. And we're going to pretend like it's okay, and it is okay, to have all the mass just centered there. So all the mass of that rectangle can be thought of as being centered at its center of mass, which is its center. So if all the mass is there, well, the mass is still the same, right? It's still 4 minus x squared times x squared dx. And the lever arm is, well, it's at the center of the rectangle, which is half as tall as the height of the rectangle. That's how you're getting half of 4 minus x squared. That's how far it is from the x-axis. Why didn't we do this for the previous problem? You mean the previous problem on the other side or the previous moment? We did. I just erased it. So we did one way we did it was we did it using a horizontal strip and said, okay, using a horizontal strip, we can do it the nice way, where it's the mass times the lever arm, and the lever arm is just y. But then we did do it the other way on the other side of the board, which I've erased. But you can go back and watch the video later when I post it, where we said, oh, you can also do it as that the height here. So instead of doing the mass times the lever arm x, or on this axis, we did the mass times the lever arm, and the lever arm was 1/2 times the top function plus the bottom function. We did that instead. And it ended up being, so what ended up working out is you get 1/2 this times this is what you're integrating, which simplifies to 1/2 the top function squared minus the bottom function squared, which is exactly what we have here. We have 1/2 the top function squared, the top function squared, right? 4 minus x squared times 4 minus x squared minus the bottom function squared, but the bottom function is 0, so it's not showing up. But we did do it the other way. The reason we have to do it this way here, unlike the previous problem, is because here your density is a function of x. And if your density is a function of x, your integral has to be in terms of x. You cannot do it in terms of y. Right? I can't say that the moment around the x-axis is the integral from 0 to 4 of the mass of this, which is the right function minus the left function. So the mass would be, let's see, x equals positive square root of y minus 4 minus the negative square root of y minus 4. So that would be the area of that, but then the density is x squared. And the lever arm is y. But the problem is you can't change the density to being a function of x to being a function of y. It just doesn't work. So we're stuck doing it this other kind of less nice way. Let's see what we get though. We multiply it out. So I got 1/2 the integral from -2 to 2. Okay, let's multiply it out. So 4 times 4 is 16x squared. And then minus 4x squared minus 4x squared is minus 8x squared times x squared is minus 8x to the 4th. And then minus x squared times minus x squared is x to the 4th times another x squared is x to the 6th. Oh, that's going to be gross. So then again, I notice that this is an even function. So I'm going to double it and go to 0. So this ends up being, that does cancel, 16x cubed over 3 minus 8x to the 5th over 5 plus x to the 7th over 7 from 0 to 2. And when you plug in 2, so here's something that's kind of nice. 16 times 8 is 128. 3. 8 times 2 to the 5th is 256. 5. And 2 to the 7th is also 128. And this is not, I mean, it's pretty heinous, I'm not going to lie, but it's not so terrible. You can totally factor out 128. If you factor out 128, you're left with 1/3 minus 2/5 plus 1/7. And we can get a common denominator, and it's still awful. So a common denominator would be blah. So let's see, fine. This is going to be 5/15 minus 6/15, yeah. So I've got negative 1/15 plus 1/7. So that's going to be negative 7/15. Sorry, negative 7. 7 times 15 is 105. Plus 15 over 105, which is 8 over 105. So we end up with, oh my gosh, 128 times 8 over 105. That's our moment around the x-axis. Okay, and now, finally, I will point out a lot of these moment calculations are terrible. But finally, our center of mass, our x coordinate was 0. Our y coordinate is the moment around the x-axis divided by the total mass, which in this case was the moment around the x-axis was, where'd you go? This terrible number here, 128 times 8 over 105 divided by this, 128 over 15. So let's flip and multiply. It does turn out to be kind of nice. Times 15 over 128. 128's cancel. 15 over 105 reduces to 1/7. Right? 15 times 7 is 105. So we get 8/7. Interesting. So definitely, right, more of it's on the bottom. Right, or I should say, right, from 0 to 4, 8/7 is barely, a little more than 1/4 of the way up. So there's a lot more mass down there because there's a lot more area down there. All right.
James?
Yeah.
I had a quick question. So when we're calculating our m sub x, does that indicate that we're rotating or going around the x-axis or
Correct.
y?
Correct. Which is why it's the coordinate for y bar, because you're asking where in this direction am I going to balance? So what y coordinate am I going to be on so that my tendency to swing either way is 0?
Okay.
Yeah, good question. Okay. So yeah, let's do another example. So again, centroids are just the geometric center. And we make the assumption that the density is constant, which we know means the density will cancel out. So let's find the centroid of this. So centroid of the region that I'm going to draw here. You've got y equal to sine of x. Sure. You've got y equal to sine of x. You've got y equal to 0 between 0 and pi. And I want to find the centroid, which is probably right about there. Can anyone tell me what the x coordinate? Oh, excuse me. Can anyone tell me what the x coordinate is? Or type it in the chat.
Would it be pi over 2?
Right. Why? Symmetry. So if you have a shape that is symmetric about an axis, that axis is where one of your centers is. So if someone gives you a circle, the centroid of the circle is just the center of the circle. Or someone gives you a square, the centroid of the square is just the center of the square. So any shape that's kind of symmetric about the both x and y kind of axes has its centroid at its center. On the other hand, a triangle, its centroid is definitely on the lines. Like if it's a isosceles triangle, right? Its centroid is certainly on the line that cuts it in half there, but then that one is not as clear. So yes, the x coordinate is definitely pi over 2. The y coordinate, on the other hand, we have to find. And we have to do this formula that I'm not a fan of, right? We have to do, okay, so we're going to use, oh, actually, no, well, so we could do it let's look at both ways of doing this. So here's the not fun formula way. Vertical strip. So we need to find the mass too. Let's find, or I should say really the area. Right, so the mass is the integral of the density times the area. But we know the densities are going to cancel. Let's just say the density is 1. Totally valid. So that's just going to be the integral of sine of x dx. Right, that's the area of that rectangle is the height times the width from 0 to pi. You're going to get negative cosine of x from 0 to pi, which is negative cosine of pi minus negative cosine of 0. Negative cosine of pi is negative 1 plus cosine of 0 is 1, so you get 2. So the area of that shape is 2. The mass of that shape is 2 times the density. Okay, let's find the moments around the x-axis. So one way to do it is using the formula where it's 1/2 the integral of the function squared. Really the top function squared minus the bottom function squared. Right, really I'm saying it's the, so let me talk again about where this is coming from, right? This is the integral from 0 to 1 of the mass, which is the density times the area. That's our mass. We're setting the density equal to 1. And then the lever arm, well, again, we're going to say that this is all centered at the center of that. So the lever arm is half the length of that strip, which is just going to be 1/2 of sine of x. That's how we're getting this. 1/2 sine squared dx. Okay. Yeah, no, that's really, so you could try and do this another way. The problem is if you're going to do it using a horizontal strip, you got 2 problems. Problem 1, if you solve for x in terms of y, you get x equal to the inverse sine of y. Problem 2, the right function and the left function are the same function. So you have to kind of, it's really problematic. You definitely don't want to do so because yeah. I'm just gonna leave it at that. You don't want to do it this way. So we'll do it this way. We got to integrate 1/2 sine squared. Oh, how do you integrate sine squared? Well, there's a really silly way of doing it where people use integration by parts, which is not what you should do. There is an identity for sine squared. There's two identities for sine squared. One of the identities is that sine squared x equals 1 minus cosine squared x. It's not the identity we're going to use. The identity we're going to use is that sine squared x is equal to 1 minus cosine of 2x divided by 2. That's the identity we need to use here. So this is going to be 1/2 integral from 0 to 1 of 1 minus cosine of 2x over 2. I'm going to factor out the 1/2. So I'm going to get a 1/4 integral from 0 to 1, not to 1, to pi. Oh my goodness. Of 1 minus cosine of 2x dx. Okay, let's integrate. The integral of 1 is x. The integral of cosine of 2x is sine of 2x divided by 2. Plugging in pi, I get 1/4 of pi minus sine of 2 pi is 0. Plugging in 0, I get 1/4 times 0 minus sine of 0 is also 0. So I get 1/4 pi. So then my centroid y coordinate, y bar, is going to be mx divided by the mass, which is 1/4 pi divided by 2, which is pi over 8. A little bit bigger than a third. Seems reasonable. I was looking at something here. Okay, sorry. I was like looking at the same thing that I said words that made me think I was doing something silly. Okay, we got 15 minutes. Sure. I feel like we should talk about Pappus's theorem for just a second. So,
wait, James.
Yeah.
For your very last, like, for the bottom right, like 1/4 pi minus 0. How come it turns into minus 1/4 over 0? 1/4 times 0.
Well, right, I'm plugging in my limits of integration. So when I plug in, this is from 0 to pi.
Mm-hmm.
So when I plug in pi, I get pi minus sine of 2 pi over 2. But sine of 2 pi is 0. So I get pi minus 0. And then I subtract, and I plug in 0.
Oh, okay.
0, I get 1/4 times 0 minus sine of 0, which is 0.
Okay. Thank you, James.
You're welcome. The other thing you can use centroids for is to find volumes of revolution. So let's take a look here. Yeah, we can do this. Okay. So let's say I wanted to find the volume of that shape, sine of x, revolved around the x-axis. So I want to find same shape, right? Y equals sine of x. I want to revolve it around the x-axis. So it'll look like this. It's kind of like maybe a seed shell or something. Okay, so I'm going to use the disk method, right? Now it's funny because using the disk method here, we're going to see kind of the same integral, I think, right? So using the disk method, the volume is going to be the integral of pi times my radius squared dx from 0 to pi. Cool? Cool. Well, that's the integral from 0 to pi of pi times sine squared x dx. And my radius is sine. I think we just did that integral. Well, we almost did that integral. we did 1/2 of that integral. And 1/2 of that integral was equal to, well, let's just say the integral itself was pi over 4. So this here is going to end up being pi times pi over 4, which is pi squared over 4. We could have done the work, but we already did the work. And now here's what Pappus's theorem says. Pappus's theorem says that you can instead kind of imagine all of your area of your region at the kind of center here. So if I take my region and I think about where the centroid is, so the area of that was 2, right? It was 2. Yeah, it was 2. And the centroid here is at pi over 2 comma pi over 8. So what you can do is you can say, well, I'm going to take all that area and just see how far all that area travels. So if I think about, well, how far is the centroid going to travel? The centroid, if you rotate that around, the centroid travels 2 pi times what I'm going to call, in this case, y bar, right? The distance from the x-axis. 2 pi times y bar is 2 pi times pi over 8. Which I feel like I'm missing something here. Sorry, I am missing something that's. What am I missing? So let me just double check. No. Sorry, I'm just making sure I didn't make a stupid error here. Sorry, brain. What did I do wrong here? I did something wrong. Sorry, 1 second. I'm making a dumb mistake and I'm not seeing it. What am I? Oh. I see what I did. Sorry. So here's the mistake I made. I was trying to use a shortcut and I was not careful. I was trying to say that this integral, that integral is equal to this. And now I factor out the 1/2. So when I got 1/4 pi, I forgot that I was including the 1/2. So this is equal to 1/2 times 1/2 pi. So this integral is actually equal to 1/2 pi. Sorry, that's kind of lame. I apologize. So this volume integral should have been pi times pi over 2. Sorry about that, guys. Okay. So the volume of that's actually pi squared over 2. Okay, but now here's what I was trying to say before I got stuck. The centroid travels the circumference of this circle, which is 2 pi times how far it is from the axis of rotation, which is what y bar is in this case. So that's going to be pi squared over 4. So then the volume is equal to how far the centroid travels times the area of the region, which in this case is pi squared over 4 times 2, which is pi squared over 2. So that's the idea about Pappus's theorem, is that you can find the volume of revolution by finding the centroid and then asking how far is that centroid going to travel and multiplying that by the area. So enough, if you wanted to instead go around the, say, y-axis, well, again, we can find the volume very easily. The area is 2. The centroid is pi over 2 from the axis of rotation. So the centroid is going to travel 2 pi times x bar, which is 2 pi times pi over 2, which is pi squared. So then the volume is going to be the area times how far the centroid traveled, which is going to be 2 pi squared. So it's usually not easier to find the center. Well, that's not true. Sometimes they're going to give you a shape that's like super easy. So for example, someone could say, all right, so here are some hard volume questions that are easy with Pappus's theorem. What's the volume of the circle of, volume of the solid obtained by revolving the circle x squared plus y minus 3 squared equal to 4 around, I don't know, let's make it stupid, the line x equal to 5. This would be a very, maybe not, no, this would be a quite challenging problem to do the regular, right? So first of all, right, you have your circle, which has a center of 0, 3, a radius of 2, and then you'd be going around the line x equal to 5. And you can use the disk or the washer method, right? But you have to, like, if you're using the washer or the shell method, you're using shells, right? You could do the integral of 2 pi times your radius, which is 5 minus x, times the height of your strip, which is the top function, which is terrible. It's 3 plus the square root of 4 minus x squared minus the bottom function, which is 3 minus the square root of 4 minus x squared dx. That looks really terrible. I don't want to do that. I don't have to do that because here's the thing. The circle, there's the centroid. How far is that centroid from the axis of rotation? Oh, it's 5. Great. How far is the centroid going to travel? So the centroid travels 2 pi times its radius, right? We're going around like this. Well, that's easy enough. That's going to be 10 pi. What's the area of that circle? I know the area of a circle. The area of the circle is pi r squared, which is going to be, well, the radius of that circle is 2. So it's going to be 4 pi. So the volume of this circle revolved around the x equals 5 is going to be 10 pi times 4 pi, which is 40 pi squared. Super duper easy with Pappus's theorem. Super pain in the ass without it.